All right, so like I said, we're going into mod 2's section, what did you say, guys? I can't remember now. 21, right? We're on section 21. So I think it's called Combinatorics and Maximum Likelihood Estimation, or MLE for short, which that title is just super long, right? But just know that's what we're talking about. So we're going to break this up into conditional probability, which is what we're talking about here, and then into maximum likelihood estimation. And I just closed it, but let me show you guys real quick. So I just wanted to quickly show that for section 21, again, as always, the curriculum has a lot more detail than I'm going to go into, but I'm going to show you guys basically more of the notation. It's really a continuation from back in module 1 with our probability and statistics. So like think like section 9, section 8. So just kind of know like it's kind of like a continuation here. But conditional probability, which we'll talk about just in a second, basically goes from about here to down to Bayes' theorem. I'm not going to talk too much about Bayes' theorem just because we're going to touch it again later on for classification. So, but just know Bayes' theorem is a very important theorem. Basically, it's the basics or the basis of like statistical classification. It's kind of like a really powerful tool. But we'll talk about this again, I think, on Fridays when we talk about section 22. But just know that's there. Now, maximum likelihood, which I have coming up after this, like a separate notebook, essentially just these two sections are lessons. And it seems like not very much, but I want to make sure you guys go through because maximum likelihood can be, the derivation can be kind of confusing, even for people who are seasoned with mathematics. Just understanding like what exactly are we trying to achieve. So I'll talk about that in a second. But just wanted to show you guys where that falls in the curriculum. So conditional probability, let me just make this smaller to make it more organized. So we kind of talked a lot about this stuff. I'm going to reiterate some things. So conditional probability, we talked about sample spaces. So remember, sample space is basically just the space of all possible events, right? So the only things that are included in a sample space are things that can happen. So for example, a die, you can roll 1 through 6, but you can't roll like a 9, right? That's impossible for a die. So it wouldn't be part of the sample space. You can also have continuous sample spaces. You can basically like imagine like throwing a dart at a dartboard and landing on the dartboard and basically having like something along the lines where it can land anywhere on those points. That's a continuous sample space. Those are mostly what we'll represent visually just because they're easier to represent. But basically just the sample of all things that can happen, okay? So this kind of leads us into independent dependent, which I think we talked about a little bit, but we're gonna formalize it. So when we say something is like an independent event, what that means is that if this happens, if one thing happens, like let's say event A, and event B happens, whatever happens with event A does not affect event B. So one way you can think about this is rolling 2 different dice, right? So like if you roll 1 die and you get like a 6, right? And you roll a second die and you get like a 5. It should hopefully come to reason that rolling 1 die and then rolling the other die, they don't affect each other. They're independent from each other, right? You can separate them out completely. Versus something that's might be a little different, like I'm trying to think of something that would be like kind of a weird die where like maybe like if you rolled a die and like it got chipped on one end, that now all of a sudden the probability of you landing on like a 4 is higher. Like that would be a non-independent events, right? Those would be dependent events. So the way we kind of like formalize this is through this basically mathematical representation. And so I wanted to show you guys this because it shows up in the curriculum a lot. I'm trying to remember if we actually specifically did this. Like, I don't know if you guys remember seeing this formulation, this written down. Just sometimes if we've seen this before, thumbs down, you're like, I don't really remember seeing this at all. Okay, so so we've done this a little bit, but I'll just kind of do a quick review. So we talk about like event A and event B, and usually we represent probability as a capital P. Sometimes in certain textbooks, you know, in certain texts, they'll reference as a lowercase p or even PROB, right? But for the most part, usually we say capital P. That's pretty standard saying that's the probability of event A happening, okay? And event A is kind of like this sample space, like all these different events of A, okay? So essentially when we say something called an intersection, okay, which is represented by this upside down U, okay, when basically it's like the sample spaces of A intersect with sample section of B, okay? If those intersections are basically just being multiplied, that means it's independent. This also has a property of saying when we have a union, this is what this U comes through. Basically, if we combine the sample space of A and B, which is represented by this brown like two kind of masses stuck together, is that essentially what's happening here is that it's the probability of A plus the probability of B subtract that intersection, PAB, or PA intersecting, dang, I can't talk, PA intersecting B, right? So basically it means that we don't double count, is that, and that is actually the definition for our independence. And so just know that essentially hopefully this like makes sense when we say like, oh, if these are independent, the intersection shouldn't affect each other in that sense. So you essentially just aren't double counting. Okay. So, but that's what and I think this is actually directly from the curriculum too, is that this guy right here, this is the visual representation of this mathematical formulation. Okay. Any questions on connecting this to this? Cool. All right. So our next definition is something called a disjoint, which I think we actually talked about before too. But basically a disjoint you can think of is that like they're not connected. You know, they're disjointed, right? They're not joined together. And so when we have something like that, that's something actually different from independence by itself. But essentially it means that if we take the union of A and B, we actually just have to add the probabilities of A and B, which you think of it this way. If we added the probabilities of A and the probability of B, right, you actually would get this double counting part. So disjoint actually says that there is no overlap. There is no way you can double count. Basically, we can just simply add the sample size of this one and sample size of that one. And basically by able to do some mathematics, we can actually kind of rearrange some stuff. But I did want to kind of point this out that the curriculum shows right here, which is the PA, and then you see the slash, like not slash, but like kind of like this straight line, and then B. What this is read as is the probability of A given B. Sometimes you might hear it as such that B or something along those lines, but usually it's saying like, what's the probability of A happening given that B already happened or B is going to happen? So I'm trying to think of a good example of this, but one thing you can say is like, what's the probability of it raining given that there are clouds outside? Okay, so like obviously the probability of it raining is going to be different if there are clouds outside than there are no clouds outside, right? So that's kind of like the idea of like saying A given B. So the probability of, hopefully you can get that, as like the probability of rain happening is, given that there are clouds outside, is higher than the probability of rain happening by itself, right? Because you're basically narrowing in a more case. In that case, essentially what you're doing is you're saying that basically, this is the kind of definition of our not disjoint, but basically this is one of our definitions, is that we can say the probability of A intersecting B divided by the probability of B is just this guy right here. And this is actually coming into Bayes' theorem, which we'll talk a little bit about, but just know that I wanted to give you guys this vocabulary where this is probability of A such that B, or probability of A given B, and this is read as probability of A intersecting with B. It's just the probability of B. Okay. There's a lot of letters being thrown around, but hopefully that doesn't seem too complicated. Again, these are just a visual of this formula right up here. And you can see that's pretty, like, what's funny is like a lot of time probability, you kind of like look at it and you're like, yeah, that looks really easy to understand. But obviously this is just a formulation to be able to rewrite this information out. Okay. So this leads us to a few theorems. Okay. So the first thing is basically the product rule. And so these are basically like how we deal with probabilities. So this right here is basically saying this is true for all sample spaces, is that the probability of A intersecting with B is just simply the probability of B times the probability of A such that B. And you can kind of see is that if we take this part right here, this probability of A given B, that's this right here, which makes sense. You can kind of see mathematically, if I just took this part and kind of moved it down into that equation, it'd be probability of B times probability of A intersecting B divided by probability of B. Well, probability of B would be canceled out, and then you would just be left of PA intersecting B, and that's what this is right here. Okay, if they were independent, okay, then basically you wouldn't have to worry about the probability of A and B, because they're independent. We can just say this is true, right? So this is our definition of our probability, is that if they're independent, we just say, hey, A intersecting B is PA times PB. And you can see here, you can essentially just replace this into here, and you wouldn't have to worry about probability of A, probability of B. We can essentially just pull that part directly out. Essentially, this is just probability of A. Because hopefully that makes sense, is that if they're truly independent, it doesn't matter whatever B is, right? So, for example, saying the probability of it raining given that Adam has a cold. Well, that's probably a good one. Let's say the probability of it raining given that, I don't know, if the Warriors win the finals. Like, that should not be related in those ways. So you can kind of think of it like, okay, like, though you wouldn't, given B, it doesn't matter. So it's just the probability of A happening. So that's kind of like that concept here, if they're independent. So basically, this is the general form of the intersection. But if they're independent, it simply simplifies to the probability of B times the probability of A. Okay, cool. Makes sense? Thumbs up if that sounds good. And again, this is more like formalizing mathematically. Yes, I'm shaking there. Yeah, that's okay. This is mathematically just kind of expressing things that you probably intuitively understand. It's just much more like trying to make it formal, so that way we can actually do some mathematics with it. For example, when we do like Bayes' rules or Bayes' theorem, we can actually say, oh, the reason why we can say this is we can mathematically show this thing. Okay, probably is kind of weird like that. And also, this notation is really useful. Just know that it's given or such that, or, you know, depending on who you're talking to. Okay, so again, this is just the general product rule. This is true for any sample space. It's just that if it's independent, this essentially just simplifies to the probability of A, since it doesn't matter if B doesn't affect A at all. Same thing for this one. This would simplify to the probability of B, since A doesn't affect B at all. Okay, so this leads us to the chain rule. So the curriculum kind of shows a little bit of this, and so I'm not going to like go into it, but I just wanted to show you like all this going through. Yeah, I saw Eric's eyes there, like saying like there's a lot going on here. But you can see here basically is that as we do more and more intersections, we can essentially start breaking it down further and further. So you can kind of think of this as like one, the way I think about this is this like one big probability, like, or one big sample space, because that's what basically intersecting B and C together is, making one big sample space. So what this is doing is exactly this. It's like, okay, well, probability of A, so you can think of this part, probability of A given that B and C with the probability of B and C, okay? And I'll say and when I say intersection. That's kind of usually what the notation tends to be. But basically it's like, oh, if we combine these together, this is basically, you can replace with like the letter, in this case for here, you can replace it with letter B, and you can replace this part right here with letter B. And that would be the same thing as this part right here. And then we can simplify it in a different way. We could, instead of doing like A given, oh, I'm sorry, we simplify this further. We simplify this part, because it's a chain rule. Say, okay, well, the probability of B and C was just given from here. So it's probability of B such that C times the probability of C. Okay, and that's part. So basically you're just kind of breaking things apart. So I'm just kind of showing you a little bit like where this notation's going. And obviously you can kind of make this, this can go as far as you want. It can be A, B, C, D, E, F, however long you want. And this chain rule basically would continue on further and further and further and further. The nice thing is that if the space C is disjoint, which is why we love using disjoint spaces, is that this simplifies essentially because this B and C right here, if you remember the disjoint, that's just simply adding up the probability of A, probability of B. So we can simply just say, oh, probability of A times this guy times this guy and all and such. And basically you would get a simple, basically, probability of each part being multiplied by that simple, see, I think this is, I just realizing this now. Okay, yeah, this is just saying this is not correct. I think I must have miswrote this down. Ooh. But this should be the intersection of like C1, C2, C3, C4, and going forward. You're simply just adding up the probabilities together. Okay, cool. Yeah, so anyway, that's the chain rule. Curriculum goes through it a lot longer than this, but I just wanted to show you at least what that is. Basically, you're just breaking it down further and further using this rule and possibly disjoint rule. Okay, cool. So that leads us to Bayes' rule, Bayes' theorem. And I'm just going to give you a little bit of vocabulary, is that in the curriculum again, it talks about this. This is actual Bayes theorem, Bayes rule, which is really interesting story is that Thomas Bayes is the person who's named after, actually developed this thing, and he actually thought it was so obvious that he like didn't even like publish it. He was kind of like, oh, well, yeah, duh, like this is just true. Which, if you ever hear an explanation for it, it's like, oh yeah, it is kind of true. It's basically it's that you can figure out given A such that B, you can have the other part, and you can say this like in verbal terms. And basically, what it comes down to the fact is that if you have more information about one thing, you can gain information of the whole. So the way he kind of talks about this, he actually never wrote down this equation. Interesting enough, that like this theorem, this rule that he wrote that's famous with his namesake, he actually never wrote it down, which is kind of interesting. But the main thing like here basically is that you can get information, and I won't go through the whole equation because we'll talk about this again later, it's in the curriculum. But basically it's like if you have something called a prior, what your prior knowledge is, you can basically infer your posterior knowledge. Okay, and then your probability of B such that A is going to be thought of like the likelihood of B happening, such that A is happening. So what he basically had, this is a famous experiment where he basically sat on his chair, he had a table behind him, and he would literally throw a ball on the table, and he have assistants, you know, say, well, assuming it landed on the table, he would throw multiple balls and say, was that ball closer to that one? And assuming it's random, basically he could kind of figure out and hone in where his original ball was thrown at by basically saying, well, if it's closer, it has to be on the table. Well, if it's closer versus randomly, like where did that go through? Basically, it's kind of like using like new knowledge to update your, like we call it a belief, but basically you update what your current knowledge is or what you know at most. And as you get more and more information, you can basically update, you know, what you think the truth actually is and get closer and closer. That's essentially what Bayes' theorem is doing. I'll leave this for another time, like when we talk about it on Friday, but also it's in the curriculum, but we'll talk about it again, section 22. Okay, cool. So I'm gonna breeze right through that. It's actually super important, but I am just breezing through it. Okay. And then we have partitioning. So just partitioning, just know that you basically can split the events into different sample spaces. I did have an original note on conditional independence. You can see it's blank right now. But basically there's a specific, actually I don't know if this will link over. Yeah, that won't link over right now. But there is a part in the Learn curriculum that talks about conditional independence of making sure, it's kind of like the correlation versus causation, is making sure you don't work backwards. Just make sure you read that part right here. I think that's in the first, I guess I can pull it up, but this is just a note on conditional independence when they introduce Bayes' theorem, is making sure you don't work backwards. You have to kind of move forward through. It's kind of like when people associate bad things happening, you know, with something that had happened, but they're completely independent from each other. They're not one causing the other, or which way, like, for example, the probability of like you being sad on rainy days might be higher, but does your sadness cause rainy days? Well, you probably know intuitively, no, that's probably not true, right? Like it's probably the opposite, where it's like, oh, rainy days are causing your sadness, or at least they're related in some way. This is what conditional probability independence have to be, and you have to be kind of careful of like saying, okay, which direction? Because in that case, it's pretty obvious, but when you're doing these kind of tests, you have to kind of be careful. It's like, wait, am I assuming one thing causes the other, or am I just assuming at the opposite direction? And that's where Bayes' theorem can kind of, I think people tend to misinterpret Bayes' theorem if they're not careful. So definitely read that section in the curriculum that shows up, and you'll see it right there. There's a little picture of like a person under a rain cloud, essentially. Okay, so that kind of sums up like my quick thing of conditional probability. I just really wanted to show you the notation. The curriculum does a good job actually explaining parts and walking through it. But I wanted to at least show you guys the notation here with this intersection and just the fact that you can break things apart depending on your different assumptions. So any general questions that you guys might have? I know I walked through it pretty quickly. Okay, cool.